How many commands or instructions are truly necessary to program whatever we want, from a calculator to an operating system? What is the minimal set? Let's think about it. We surely need to be able to access and modify the memory. We talked about the memory in the previous video. For this purpose, the equal sign can be used. Like that, we have a equal to 5, which means that we have some dedicated piece of memory labeled a, and we are going to assign number 5 to it. The second line, b is equal a, means that we should read the a, whatever is stored there, and assign the same value or save the same value under the label b, where again the b is some named place, some named space in our memory system. Perhaps we can include some arithmetic operations. Here we have c is equal a plus b. That's pretty cool. The result in this case will be 10. And again, I read from the memory, I read a first, b the second, and sum it together. Save the result to another memory place called c. It still doesn't do much, so what if I want to add print to write something on a screen? Hello world. Very nice, so is this enough? In fact, we don't even need the last one. To properly answer this question, let's discuss Turing machines and Turing completeness. Alan Turing is a very important name in computer science. He was a British mathematician and logician. We have a movie about his life, which is not 100% accurate, but it's accurate enough. He is considered the father of theoretical computer science and artificial intelligence. His work was crucial in breaking the Enigma code. He developed the concept of Turing machine. We are going to talk about it. He described it in paper published in 1936 on computable numbers. So what a Turing machine is, it's a model, it's a mathematical model. It consists in infinite tape and a head. The head can read and write cells on a paper, which is a tape. It also contains finite set of states. It can process basic instructions where the instructions are defined using transition rules. Let's dive into the components. The tape. Imagine the tape as an infinite stripe of paper. The tape represents memory, and the memory in Turing machine is unlimited. We are talking about models, so it's not necessarily realistic. Second thing is head. The head can move left or right. It can also read what's written on a paper on a particular cell below it, or it can erase it and write something different there. After that we have states. This is literally a set of numbers. Important thing is it's finite. It has some certain length. Lastly, we have transition rules to specify how it's going to move between the states. We usually call them delta functions. Let me show you how this thing works. I'm going to use my own implementation. Link to the source code to my GitHub will be in the description if you want to experiment by yourself. My Turing machine has a simple visualization, and it can load and process any program you want. The program can be specified in included JSON. I will open it. Here you can see function addition of binary numbers as a simple example. We have some finite set of states. We need to define what is a start state. So what is like the first state the machine is going to use. The interesting thing what you can see is that the last state, there are numbers, but the last one is called age. This is a symbol used in this world to specify halt. It means that the machine reached its end. Better to say the computation finished. The syntax of it is pretty easy. First of them is ID of a state. Second is a symbol what we are going to read in this particular cell below the head. And the other three numbers specify new state we are going to switch to. The second number says what we are going to write to the tape. And the third one specify if the head is going to move one right or one left. I use three characters here, 0, 1 and underscore. The underscore is used for nothing, nor 0 nor 1. Let's interpret the first line. It means that if machine is in 0 state, reads character 0, stay in 0 state, write down the 0, means do nothing, and move head 1 to the right. Let's run it. I have binary number 5, 101, and binary number 6, 0110. The red arrows symbolize head and the character we are currently on. I'm at state 0, and the program even shows what transition function or what delta function we are going to apply in this particular step. As you can see, it shows the second one. We are in state 0, we are reading character 1. It means that we stay in 0, we are going to write 1 down, and we are going to move the head to the right. So I press spacebar to step, and that's exactly what happened. Let me just go through. I reached the halt, the computation ended, and we have our result. 1011 is binary for 11. Turing machine can theoretically execute any program given enough time and resources. That's very important. We have unlimited memory, thus unlimited resources. And the time is also not a concern here. Don't forget, we are talking about model, not about real device. This brings us to an assertion. If your system can perform all functions Turing machine can, it will meet all your needs to describe and execute any program you want. This concept is known as Turing Completeness. We say that the system or programming language is Turing complete if it can simulate everything what Turing machine can. This implies that Turing Completeness doesn't guarantee anything regarding to runtime or memory usage. Also, there are some problems that Turing machine cannot solve. The most commonly discussed one is probably the halting problem, which involves determining whether the current program will halt or continue forever. It really means that it cannot distinguish between some infinite loops or unsolvable problems and tell you in advance if there will be a result or not if you wait. It's important to say that the common programming languages are Turing complete, such as Java, C++, or Python. What is a programming language in relationship to Turing machine? The programming languages are abstractions over the Turing machines. They provide higher-level constructs, so there is no need to think about the head and left and right movements. Let's get back to the question from the start. What is a minimal set of the things what we need being able to program anything we want? If we take Turing machine as our thing we should try to reproduce, well, it's not so much. We definitely need some conditional branching. If we are in state 0 and read character 1, we should jump to state 1 and write character 0 and move our head right or left. We can also use goto. Simply something which allows us to choose which part of the code will be executed and which part of the code will be skipped. We need repetitions and some sort of iterations. We should be able to move +1, +1, +1, -1, -1, -1. Also, we are able to write cycles in Turing machine very easily. This is one of the reasons why the halting problems exist. It means that we can skip from state 1 to state 2, and we can skip back from state 2 to state 1. And we can repeat it as many times as we need. So yes, we need cycle. This is usually implemented as for or while. And the last thing is reading and writing from and to the memory. That's what the head does. It can read and it can write. You should realize one thing. We also need some specifics in hardware itself. There are probably two. First of them is being able to sequentially run instructions, one by one. And the second one is memory, which is not accessed sequentially. It simply means that we are not forced to write something left or right. You could see, for example, in binary numbers that we can move our head 1, 2, 3, 4, 5 times and do something with character there. This type of memory is called random access memory, RAM. And as you know, your computer have it, your phone as well. And that's about it for today. As you can see, the number of commands what we really need is not that high. In determining what we need and why, the Turing machine is an answer. If you would like to know details, you can definitely study the Turing paper. It's great. And obviously, if you want, you can leave a comment and we can go through the paper together. Last thing. Because for this exercise, you have the source code available, I challenge you to experiment with it. You can really try to specify your own program to a JSON. The binary addition is that as an example. You can think of your own delta functions, or you can check internet for something interesting. Just write it there, write the program, and try what's gonna happen. There are actually two important JSONs. The first one is with the program itself, and the second one is with the input data, so you can easily distinguish. It's actually pretty cool. You can even take my binary number addition and try to feed different data using the second JSON, and you will see how it works. I'm really excited about your experiment, so if you would like to share, drop the comment. I would love to see. That would be all for today. I hope you learned something and see you next time.